Welcome everyone to our second session of the Photonic webinars from the ALUVia Project. The ALUVia Project aims to realize aluminium oxide waveguides that can be used across a large range of the optical spectrum for an equally large range of applications. Today's webinar focuses on sensing applications, and we are honored to have Professor Juejun from MIT and Jerome Michon from INSPEC speak to us today. But first, let me give the floor to Professor Sonia García Blanco, the lead of the ALUVia project, and she will tell a bit more about the ALUVia technology and its goals. So Sonia, please feel free to share your screen and tell us more about the exciting technology that you are developing.
Thank you very much, Björn, for the very nice introduction. And I'm going to try to smoothly share my screen. And hopefully it works well because I'm trying to do this that my little face appears in front of the presentation. So I hope you can see my screen and I'm getting the laser pointer. So as we saw in the introduction, in the ALUVia project, we are developing aluminum oxide integrated photonic platform for applications in the ultraviolet. And now let's see if I can change the, yes. So the goal is to establish the first worldwide aluminum oxide commercial integrated photonic platform to enable new markets in the ultraviolet wavelength region. And you can see here the different parts of the project. So we're going to develop different building blocks operating down to ultraviolet wavelengths that then are going to be packaged by our partner FIX. We're going to do two demonstrators, one in spectroscopy, and we're going to learn more about this in the presentation by INSPEC later on, and another one for ion trap quantum computers. And we're going to, of course, commercialize the platform via ALUVia Photonics. Just to give you some idea about what you can do with this platform, here you can see the propagation losses of waveguides fabricated in aluminum oxide. And you can see that due to the very big band gap, 170 nanometers, the propagation can be down to the ultraviolet with losses at 369 of around 2 dB per centimeter and at 1550 down to 1 to 5 dB per meter. You can also dope the material with rare earth ions because aluminum oxide has a very high rare earth ion solubility, and then you can have on-chip amplifiers. In this case, we show a 20 centimeter long spiral, but we can make them longer. We have made 30 or 50 centimeters, and you can achieve around 20 or even more dBs of net fiber-to-fiber gain. And you can use different rare earth ions, erbium for the C-band, thulium for the 1.2 to 2 micrometers band, and neodymium for amplification around 1064 nanometers and 1310 nanometers. But this session of webinar goes about sensing, so I just wanted to make a summary of sensing projects that we have done in the aluminum oxide platform. And basically, we have used mostly the micro-ring resonators. So you have a ring that if you couple light into the ring, if you measure the transmitted power versus wavelength, you see a dip. Then if molecules attach to the ring, then the resonance frequency will change and you have a shift in the wavelength of the dip. You can define a sensitivity, which is the variation of the wavelength as a function of the variation of the refractive index here in the surrounding of the ring, and the limit of detection, which is the minimum shift that you can detect and is related to the noise of the system. This is in passive ring, so you can see that you have some dips that are relatively broad. But then if you dope the material, for example, with rare earth ions, and you instead of having ring resonators, you have ring lasers, then these dips become peaks and they become very narrow. So you can imagine that now you could have potentially a lower limit of detection. So we have developed some passive micro-ring resonators. In this project was the GLAM project, was to detect this protein, the S100A4 protein in undiluted urine. And we demonstrated a limit of detection of around 3 nanomolar. Then we doped it with ytterbium, so we had emission at 1 micrometer, and we achieved a limit of detection of 0.3 nanometers also in undiluted urine. If you want more details, we have a couple of publications that are shown here. We did a more complicated design of these ring lasers to have more control about the different sections of the laser, and also to increase at the same time the sensitivity, but also the coupling of the pump to the laser. And we achieve a lower detection limit, and a faster detection. And something very interesting that we started working with was to, instead of detecting the dip or the peak of the laser, split the resonance of the microring resonator with a grating so that we have a split mode that both peaks of the split mode shift constantly with temperature or with bulk refractive index, but the difference between them will be unaltered by temperature and bulk refractive index. So that has the promise of reducing the noise while keeping the sensitivity. And here in these graphs, we show how this splitting stays more or less constant while the temperature of the sensor has been increased by 1 degree. And here also how the splitting stays constant when we flow different bulk refractive indices over the sensor. And the latest project that we are starting at the moment is about massively multiplexed biosensors, where we normally we will put a ring in each bus waveguide and then have a detector per ring. So what we're gonna do now is to put a lot of rings per bus waveguide. And by using a patented algorithm that we have developed, we can actually follow the shift of the different rings. And that means that if you can put 5 or 10 rings per waveguide, then you really increase and fold the multiplexing capability. So that was the summary I wanted to give you about the sensing in aluminum oxide. And I just wanted to share with you that we have 2 MPWs upcoming, one at the end of September and one at the end of December. So if you are interested in trying the technology, you can always register for these runs. So thank you very much for your attention.
Thank you very much, Sonia, for your talk. There is about 1 or 2 minutes for questions from the audience. So if you have a question for Sonia, please raise your hand or unmute yourself and fire away.
Could I actually ask a question?
Yes, of course.
Sure.
Yeah. Very, very, very interesting talk work. I'm curious, where can I find out more information about MPW and maybe look at access to PDK and how to participate?
Yes. So you can look at our website. We have there the link to the design manuals, and also you can get the PDK via our partner Lucida Photonics.
Oh, okay. Okay. Thank you.
Hi. Yeah, I have a question, if you can hear me.
Yes.
Have there been any efforts for a hybrid or heterogeneous integration of lasers on these chips, or is it typically just fiber coupled?
I could not follow the question. Can you please repeat and explain a bit more what you mean?
Yeah, have there been any efforts to demonstrate like heterogeneous integration of semiconductor lasers on chip with this aluminum oxide platform, or is it mostly just fiber coupled or gradient coupled?
So we have several developments ongoing. For example, in the European project QPIC, what we are doing is to do microtransfer printing of semiconductor gain sections onto the platform, and the partner IMEC Ghent are working on that in that project on the aluminum oxide platform. And our typical way of doing it is just back coupling a laser diode or a gain section. So just by back coupling to the waveguide. We typically do that via our partner Fix.
Okay, thank you.
Is there any other questions? If not, then I think we can move on to our first guest speaker, Professor Juejun, the John F. Elliott Professor of Materials Science and Engineering at MIT. He will discuss how photonic integrated circuits can be applied to transform chemical and biological sensing. So I would like to invite Professor Juejun to share his insights with us.
Thank you very much for the kind invitation, and I really appreciate the opportunity to be able to come here and actually address the audience here, and also seeing the exciting results that was actually ongoing in the ALUVia project. So without further ado, let me get to my presentation here. I assume you can all see the slides?
Yes, perfect.
Yes.
Okay, thank you. So what I will do here today is to give you a little bit of overview about different kind of aspects of photonic sensing work that's ongoing in my group. I will start by with a little bit of a brief introduction here. The platform we're talking about here, of course, is essentially silicon photon integrated circuits. And as a lot of you probably are familiar with, the whole idea behind it is that we want to use mature silicon CMOS technology to essentially combine different components on a chip so that we can actually eliminate alignment requirements and therefore create platforms that are actually miniaturized, robust, and potentially have better performance compared to their benchtop counterparts. This paradigm also applies to photonic sensing. And more specifically, there are actually quite some advantages when you actually apply this photon integrated circuit technology to the sensing field. I actually steal this slide from Jerome, so you may actually see that again. But I think this slide really very nicely summarizes why we're actually using photon integrated circuits for sensing applications. The first advantage here is in terms of performance. So in the photon integrated circuits, light is actually very tightly confined in a waveguide that through in-plane propagation through like a spiral shape of waveguide or zigzag shape of waveguide, we can have a long optical path length and therefore increases the opportunity for the light to interact with the molecule we want to detect. This then brings about essentially better sensitivity compared to their free space component. We can also have advantage in terms of cost by leveraging essentially wafer scale manufacturing through a standard CMOS technology, and by putting together many optical components miniaturized on a chip, we can also have essentially a smaller sensor size compared to their benchtop counterpart. So now we can turn our attention to look at what are the different sensing techniques we are looking at here using the on-chip technologies. So what I'm showing here generically is what happens if a light actually propagates through a waveguide. So if you have molecules that comes to the neighborhood of the optical waveguide, these molecules can have a different refractive index compared to the background material, which then lead to a change of the effective index of the waveguide. So we can detect the refractive index change, and this is basically what's called the refractive index sensing or refractometry. We can also look at absorption induced by this molecule here, and this will be absorption spectroscopy. So I'll be giving you some examples of work that we have done in refractive index sensing and optical absorption spectroscopy here. And later on, you'll hear from Jerome Michon about essentially some work on essentially Raman spectroscopy, where we're now instead looking at photons re-emitted from these molecules when they're excited by the instant pump light. And same thing, you can also use look at fluorescence here in pretty much the same magnitude. Now, what I will not cover in this talk here is that you can potentially also use non-optical effects to actually detect the presence of the molecules. For example, when the molecules actually absorb instant photons, the temperature actually increases. You're converting the photon energy into thermal energy. And this type of photothermal spectroscopy can actually have some advantage compared to direct absorption spectroscopy in terms of sensitivity, as well as the use of different components to detect wavelengths with high signal-to-noise ratio. Okay, so as the first example here, we are going to take a look at refractive index sensing. And again, the basic principle behind it is really fairly straightforward. You will have a waveguide. The first step is that you actually have the functionalized surface with some kind of selective coating that only binds to a target species you want to detect. And that's because refractive index detection by itself is non-specific. Any molecules come to the surface could change refractive index. So you need a selective coating to make the sensor essentially specific to the target molecules you would like to actually sense. So then if you expose it to the light, only the type of molecule you want to detect will actually attach to the sensor surface. And from that, you can actually get then the signature of the presence of the target species. So I just want to quickly mention that this is a very well-established sensing techniques. People have looked at using this refractometry technique to detect different type of species, particular biological molecules. And you've also seen some very nice examples presented by Sonia, looking at how using active resonators can further enhance the performance of a refractometry. So what we want to do here, we want to actually look at, instead of large biological molecules, we want to look at small inorganic metal ions. And this is actually made possible by using a special kind of surface functionalization coating called the crown ethers. So what I'm showing you here is actually some image I quoted from Wikipedia that basically shows the molecular structure of crown ethers. So crown ether are actually this kind of circular molecules They are formed between with essentially carbon as well oxygen to form this kind of ring structures. And the key feature of this kind of crown ether is that within the ring, there's actually a cavity with a very specific size and electron density. So what people have actually found is that each crown ether, they can be highly specific to one specific type of cations, where the cation it will actually fit precisely right into the this kind of the cavity formed by this molecules here, and this specifically is basically enhanced also by the essential charge density of the cation. Okay, so. And that's why, because of this kind of selective binding capability, crown ether has been used as essentially a molecular probe to detect the presence of different type of metal ions. So our idea was that we can actually combine this crown ether with a photon integrated circuit to enable detection of a metal ion, in this case lead ion, which has a significant practical implication because lead poisoning is actually one of the severe health concerns. And the ability to actually detect ion in, for example, drinking water is very important. Okay. So for that, we have collaborated with Professor Wang Hong's group at Nanyang Technological University. They are the ones actually developed a recipe to actually functionalize photonic integrated circuits with this crown ether here that can actually selectively bind only to the lead ion. In terms of platform, this photonic platform is developed by my postdoc Brian Sia and my student Luigi Rano. The structure is relatively straightforward. We basically have essentially a magenta interferometer. On one arm, we have opened a window to allow these molecules to come in contact with waveguide directly and change the effective index. And therefore, from essentially the shift of the interference fringe, we will then be able to determine the amount of molecules that's accumulated on the surface. Some caveat I want to mention here is that on the arm of the interferometer, we actually are putting a slot waveguide here, basically to increase the light interaction of confinement within the sensing region and therefore to enhance the sensitivity. And also, if you look at the coupler region here, we actually designed an asymmetric adiabatic coupler here so that the light we couple into the two arms here is actually not 50-50 split. There's actually a specific ratio. The reason we do that is because water, the aqueous environment, is actually absorbing at 1550 nanometer wavelengths. So we have this asymmetric coupler to essentially compensate for more of the light actually absorbed by water, so that when the two arms, the light comes from two arms, recombine at the output, they can have exactly the same amount of intensity, and therefore you can actually have essentially complete cancelling or complete destructive interference of the light at the output. And this helps to boost the visibility of the interference fringe, and therefore help to increase the signal to noise ratio. So you can see that the patch sensor here after integration with microfluidic channel, and we can then go ahead and actually calculate the performance of sensor at the first step in a buffer solution. Okay, so that that's preparing essentially deionized water without containing any kind of interfering species. So from this buffer solution, we can see that on the left-hand side, this is how the fringe would actually shift as a function of concentration of the lead ion in the solution. And then from this plot, we can actually get the calibration curve on the right-hand side here that plots how the shift in wavelengths as a function of concentration of the lead ions in the solution. So we see that we see this kind of behavior here, where towards the as you go to high concentration, you see a clear saturation behavior, and this is when you essentially get sort of like a monolayer coverage of lead ion on the surface. So the surface essentially gets saturated, so you will not be able to detect even more ion there. At the lower end, the lower limit of detection is essentially constrained by signal noise ratio in the measurement here. So from this plot, we will then be able to determine the dynamic range of the sensor by looking at the limit of detection as well as the saturation point. And we found that this technique allows us to detect this lead ion with a very large dynamic range down to less than 1 parts per billion to over 60,000 parts per billion. So this makes it quite useful to look at different type of application scenarios, both from environmental samples, which typically has a lead ion in the order of parts per billion, to maybe industrial pollutants, where you can have much higher concentration there. Well, this is only a first step. We have to verify that this technique can be quite sensitive. What about the specificity? So for that, we then look at essentially different solutions that actually contains different type of ions. On top, I'm showing you here again the transmission spectra of the interferometer as we add different type of ions onto the solution here. And what we are seeing here basically is that only when we add the lead ion, we are actually seeing a response. Any other type of ions here, we essentially see no non-specific binding of these ions onto sensor surface. So takeaway message. This technique actually is very specific or selective to only the ion species you want to detect. Now, our next step is to move a step further. Instead of using solutions we prepare in the lab, we also want to actually use environmental samples we collected from actual environment to verify that the sensor can indeed operate for environmental monitoring purposes. So for that, we have actually collected tap water. We actually also get lake water, unprocessed lake water and seawater from the environment. And then we can actually selectively add some lead ion into it and to verify the performance of the sensor here. So the result is summarized on the table on top. Just to explain it a little bit, if you look at the column on the right-hand side here, there are three numbers, where the first number is essentially the measured concentration of the lead ion. The second column here is basically the standard variation of the measurement results, sort of error bar here. And then the last column is sort of the percentage variation. Okay, so what we're seeing here is we are able to actually fairly accurately quantify the concentration of lead ion down to a single-digit parts per billion level, and we can also and the result has also been verified essentially by using benchtop inductively coupled plasma mass spectroscopy techniques to show that we have very good consistency. What we also want to mention here, what we have also verified is that we can also change the pH value or acidity of the solution, and we were still able to get very high performance of the sensor with a good consistency and accuracy. So to summarize, what we have verified here is that we have a technique now able to capable of detect down to a parts per billion level of these lead ions. It's very specific, and it can also cope with different environmental solutions with different pH levels. Okay, so that's about refractometry sensing. Next example here I'm going to discuss a little bit is actually about absorption spectroscopy. And in this case, we essentially send the light through a waveguide. And what we are looking at here is the wavelength selective absorption or the spectrum. And from that, we can then infer what molecules are present. Now, because most molecules actually have specific absorption wavelengths or absorption lines, so this actually essentially serves sort of a fingerprint that allows us to determine the presence of different species without having to use a surface functionalization coating. Now, the main issue we want to address here is actually not just the sensing element. What we want to look at is essentially the light source, as well as the light detector or the spectrometer at the other end to infer the spectroscopic signatures. So for the light source, unlike in the case of refractometry, we're looking at only a small shift of the resonance peak due to a reflecting exchange. In this case, because we are doing spectroscopy, we need a broadband light source that can cover large wavelength range. On top of that, we also need to have some requirements here. For example, spatial coherence, because this light needs to propagate in a single mode waveguide. So we need a coherent source to have a high coupling efficiency. We also need to have high brightness, as well as a small size and a good mechanical ruggedness to be compatible with integration with chip scale platform. So if you look at the common choices of different kind of light sources here, you get black body source and LED, which are not really applicable to the case of integrated photonic sensors because of poor coherence, spatial coherence. You get tunable laser, of course, but to get a broadband tunable laser cover large wavelength range, this can be quite challenging. And also, they tend to be quite bulky and expensive, involving lots of mechanical moving parts. So it has recently generated lots of interest in using essentially nonlinear sources such as supercontinuum or frequency comb as a way to generate broadband spectrum light using a single source pump laser and for spectroscopic applications. The challenge, however, if you look at supercontinuum source, is that typically the pump source is a femtosecond pump laser that can be quite bulky, and also the question about how to actually integrate this kind of light source with on-chip waveguide sensor is still open question. So that's why we actually collaborated in this case with Professor Zhengqian Luo's group at Xiamen University, where his group actually specializes in developing an ultra-compact femtosecond laser source using a graphene-based saturable bobber. So this type of fiber-based laser can actually be extremely compact. The whole laser module is of the size of only a couple of centimeters in size, so they can essentially be easily integrated with an on-chip platform. In terms of integration with waveguides, we have actually chosen to use chalconite glass as our waveguide material. So these chalconite glasses are the compounds that contain sulfur and selenium, and they are highly nonlinear materials that offers very strong nonlinear interactions for supercontinuum generation. At the same time, they also exhibit broadband infrared transparency that's ideal also as the waveguide material. So essentially, we use these waveguides for dual purposes. They both as a supercontinuum source generate broadband light. They can also essentially provide light transmission to perform a spectroscopic detection. So we were able to actually combine everything together. We have this femtosecond light source. We send it into the device here, where we essentially generate supercontinuum and also look at absorption. And then we send it on to essentially a spectrometer to look at generated spectrum. So what we've seen on the right-hand side here, this is actually a spectrum of supercontinuum. We show that with moderate amount of input power from the pump source, we were able to get a broadband spectral coverage over half an octave from about 1.4 microns all the way to 2.1 microns. So we were able to detect essentially any kind of spectroscopic signatures within this wavelength range here. And as a proof of concept, we demonstrated that we can actually detect, in this case, chloroform, which has absorption wavelengths at about 1.65 or actually 1.7 micron wavelengths. And with increasing concentration, we can also see a dip essentially at the envelope function of the supercontinuum spectrum. So this platform realized integration of light source with on-chip platform. The only thing that's still missing here is actually a spectrometer. We're still using a on-chip, using a benchtop spectrometer. So we have also looked into the issue of essentially integrating this on-chip spectrometer into something that's miniaturized on-chip. Again, this is not a new topic. People are looking into it quite a lot. You can actually get miniaturized spectrometers, for example, in this case from Amazon, which is for a few tens of dollars. The downside, however, is that a lot of these on-chip spectrometers, they tend to have much inferior performance compared to their benchtop counterpart. So there's actually some fairly fundamental reason behind it, actually due to what's called the scaling law of the spectrometers. Just quickly to look at why that's the case, if you think about conventional dispersive spectrometers, your light comes in, you go through gratings, you then split light spatially at different angles, depending on wavelength. So if you have a longer light propagation length or larger optical path length L, you can have a larger spatial separation of different wavelengths, and therefore you get higher resolution, you get more spectral points. What that means is that you have this linear scaling here. The size scales with the size of the dimensions of the spectrometer or the optical path length. Okay, so now if you want to try to minimize it, then you actually take a hit in terms of spectral resolution. So that's why a few years back, we have decided that if you want to create a small on-chip spectrometer, we have to look at a different architecture that essentially allow us to overcome this conventional linear scaling. So the architecture I'm showing here is what we call digital Fourier transform or DFT spectrometer. And what we have is basically a reconfigurable Marchand interferometer, where we have optical switches on the two arms of the interferometer that can actually steer light towards two different paths here, either top paths or the bottom paths, two different waveguide paths. So the idea is that if you toggle the first switch, it can actually create a path length difference of DL between the two interferometer arms here. If you toggle the second switch, it's 2DL, next switch 4DL, and then ADL, and so on and so forth. So now, if you want to get any path length difference that equals integral multiples of DL, you can essentially create a permutation of the switch state to get to that particular value. So for example, if you want to get to say 9DL path length difference, you will toggle the first switch, they give you DL, you then toggle the fourth switch, they give you ADL, then combine, you actually get 9DL. So the unique feature about this kind of architecture is that the number of states you can actually accommodate with permutation of switches is given by 2 to the j's power, where j is the number of switches. And this is actually really important because it actually gives us this kind of unique exponential scaling, where anytime you want to double this resolution or spectral channel count of the spectrometer, you just need to add one single switch. So because of this kind of exponential scaling, we're able to develop very high performance spectrometers within a small chip scale platform. So okay, a few years back, we first demonstrated this concept. In this case, we have a platform that actually has 6 on-chip thermal-optic switches that gives a total of 64 2 to the 6 power spectral channel count. Okay. Now, over the past few years, we have continued to work on this technology. We have actually made significant progress here. So this is actually one example of the more recent generations we have demonstrated. In this case, with the 10 optical switches and the total of 1,000 spectral channel counts that make it comparable with the benchtop spectrometer. So on the left-hand side, I'm showing you here this packaged photon integrated circuits, which is done by our colleagues at FIX. And we actually made the chip at Foundry, in this case, AM Photonics. You can see that this is actually a big chip. The spectrometer is quite small. It's only a few millimeters in length, less than 1 millimeter across. And we have also developed a customized electronics that allows us to actually control all the essentially the switches as well as the on-chip photodetector, so that we can do the essentially calibration as well as data collection all from a computer screen. And in terms of performance, we designed this spectrometer for 100 nanometer bandwidth near the O band, and we were able to get essentially a less than 0.1 nanometer spectral resolution. And everything is actually perfectly automatic. So we are now actually working on a graphic user interface. So this will be a quite easy to use sort of product that anyone can access just on the computer screen. So without further ado, I'm going to summarize what I've talked about here. I have discussed to you essentially 3 technologies, including using crown ether decorated interferometers for detection of lead ion. We talk about integration of broadband supercontinuum source with on-chip sensor, as well as the on-chip compact high-performance DFT spectrometer for spectroscopy interrogation. Before I summarize, before I end up, I just want to acknowledge my postdoc and students who actually did all the work for the lead ion sensors. Those are done by my postdoc, Brian Sia and Luis Durano. And for the spectroscopic sensing work, they're done by my postdoc, Diana Mojahid, as well as my student, Martin Pieces. And I also want to acknowledge my collaborators on the project, Professor Wang Hong's group from Nanyang Technological University, Professor Cheng Chen Ruo's group from Xiamen University, as well as our industry partners, Neonel Labs, as well as Lightchip. So with that, I'm going to wrap up my talk here, and I'll be happy to take any questions. Thank you.
Thank you for your presentation. Very interesting. We have time for maybe 1 or 2 questions from the audience. So if you have a question, feel free to unmute yourself.
I have a question. What waveguide technology do you use for the DFT spectrometers?
Okay, yeah, thank you. So in this particular demonstration, we're actually using silicon, just SOI technology. We could also, I mean, it's a fairly generic platform, so we could use it to other platforms as well, such as silicon nitride. Silicon does have the advantage that it has a large thermal-optic coefficient, so you can make very efficient thermal-optic phase shifters to make its overall structure even more compact. But we could definitely do that with silicon nitride as well, and that's actually something we have demonstrated previously.
And is it possible by the design to also design it for operating, for example, in the UVBs?
Sorry, I missed the last.
Will it be possible to modify the design to make it operate down to the ultraviolet and visible wavelength range?
Yes, yes. I mean, this is quite wavelength agnostic. In
okay.
principle, you can
Nice.
operate at different wavelength range.
Nice.
Yeah, if we
you.
have the waveguide platform like aluminum oxide.
Exactly. Thank you.
Yeah.
Is there another question? If not, then let's thank Professor JJ once again, and let's move on to our second invited talk. So the next invited speaker is Jérôme Michon, co-founder and CEO of Inspec, an MIT spin-off that focuses on chip sensing and specifically optical solutions, such as waveguide enhanced Raman sensors for industrial process monitoring. Jérôme, the floor is yours.
Thanks a lot, Bjorn. So I believe you can see my slides and you can see me as well, if
Yes.
if the little thing works well. Okay, perfect. So yeah, it's my pleasure to tell you about our efforts at Inspec to develop peak sensors, and in particular waveguide enhanced Raman sensors for the particular case of industrial process monitoring. So I'll try to cover today to justify the need for peak sensors in industrial monitoring at large, and particularly in bioprocesses. That's the angle we're focusing on with InSpec. Then, because of time constraint, I'll tell you a little bit about what goes into designing a waveguide enhanced Raman sensor. I'll mostly give you the results, and then we can discuss the design process in more details later if needed, and then show you some results on real-time monitoring of the production of picoumaric acid, and why we are interested in the UV range for our Raman sensors on chip. So let's start with bioprocesses and why PEAK would be advantageous. So first off, what's a bioprocess? It's something that we're actually all familiar with intuitively. A bioprocess, generally speaking, is the fact that we use microorganisms, be it cells or bacteria or yeast, to produce a molecule of interest. Just like we do when we were in fermentation, when we make beer, for example. In that case, the yeast consume sugar and produce ethanol. The product can be a molecule like ethanol. It could also be the cells themselves. Of course, beer is a simple example. Maybe more relevant, industrially speaking, would be drugs. For example, the COVID vaccines that we all relied on a few years ago were all made through bioprocesses. So very complex molecules, which would be hard to make using traditional chemical methods. And so beer and biopharma are actually just two examples. But the applications of bioprocess, of biotechnologies are much larger than that. And don't believe me, but go check it out. But many people will tell you that bioprocessing is going to change our world exactly by replacing traditional chemical methods, a lot of which start from oil as a raw material to make complex molecules, drugs, plastics, being able to recycle plastics, or things like lab-grown meat that are really going to impact the way we all live. The problem here is that this revolution in the making might never happen. And the reason is that bioprocesses work mostly, especially the very complex ones, work very well in the lab. So we're able to design new bioprocesses that can make plastic without starting from oil. But it becomes much harder when those processes need to be scaled up to industrial size. And the reason for that is because these processes are very complex, so we don't really control what's going on, and that leads to very high failure rate that prevents those processes from being economically viable at large scale, which is obviously needed if anything is going to be exploited industrially. And so our approach at InSpec is to say that we can prevent those failures from happening through sensing that will lead to a better understanding of what's going on in the bioprocesses, and therefore lower failure rates. And let's take a moment to think, why is that the case? At the heart, bioprocesses are, again, microorganisms producing some molecule of interest. And what does a microorganism need to produce the right way? Well, it's a living being, just like we would be. So it needs the right atmosphere. And what does that mean? That means the right temperature, the right pH, for example, in the case of microorganism solution. It means the right amount of food. It means the right amount of company. Enough company, of course, so they can produce a lot of molecules, but not too much company. Otherwise, they would compete for the resources. They would compete for the food. And of course, it doesn't want competition that would take away the food. If we translate that into biological terms, it means that we need to be able to control the atmosphere, the environment of the cell. So that's the biomass, the number of cells. That's the chemical environment, what metabolites are present in the cell culture, what's the temperature, the acidity, the oxygen level, the carbon dioxide level, etc. And that's where sensors can help in understanding and ensuring the right environment for bioprocesses. The problem is that right now, this sensing, this monitoring is mostly done offline. Meaning by taking samples out of bioreactors to analyze them on big bulky instruments like chromatography instruments. That leads to contamination risk because samples need to be taken from the medium. It takes longer. It doesn't allow for a real-time feedback loop again because the measurement is not happening directly inside the reactor in real time. And oftentimes an operator is needed to, again, transfer the samples from the reactor to the offline machine. And then at that point, hopefully, it's pretty obvious how PICs can help. Through their small size and their low cost and their high efficiency, they could be integrated directly inside the reactor to do inline measurements in real time that would enable real-time feedback without needing for sampling and sample preparation. And that would also be compatible with what are called single-use technologies in bioprocessing. And that's the motivation behind what we do at InSpec. We have started by using a specific chemical measurement method, namely Raman spectroscopy. I'm not going to spend too much time on the physics of Raman spectroscopy. In 2 words, we shine light on the medium that we want to analyze, and then by detecting the scattered light, we get a spectrum that gives us an indication both about the identity, so the nature of the molecules, and also their quantity. So it's both qualitative and quantitative. What's very interesting for bioprocesses specifically is the fact that it's a very specific method, so it can easily detect different molecules in a complex environment. And it doesn't require any sampling or sample preparation, and it works well in aqueous media. And that's the reason why Raman spectroscopy has already been used for probably decades at this point in bioprocess monitoring. So through acquisition of spectra pretty much in real time over, in this particular example, a span of 15 days, people are able to track the concentration of various molecules of interest, such as glucose, lactate, etc. So that was done with what I call a traditional Raman sensor, which would look something like this. So it's very much a free space interaction that happens between the light and the medium. So the light is focused by a lens at the tip of the probe here, and the interaction happens in more or less at the focal spot of the lens. And what we're doing at InSpec is that we're replacing these traditional sensors with a peak-based sensor. In waveguide enhanced Raman, the light propagates in the waveguide at the surface of the chip. And through the evanescent field interaction, it will excite the molecules in the medium and collect the Raman signal emitted from the molecules. The benefits are the traditional benefits of PICs. First of all, the cost. So something like the probe on the left typically costs between 5,000 to 15,000 euros. Obviously, we can make PICs for a much lower price than that. We can also increase the sensitivity, as JJ described earlier, through the increased light matter interaction at the surface of the chip and the long interaction path lengths. We can reach higher levels of detection. The size is obviously smaller, and there are also some more specific advantages, like the fact that the PICs are not disturbed by ambient light conditions, because the only light that couples to and from the waveguide is the light in the evanescent field, and nothing that would come from, say, ceiling light or ambient light. So that's the motivation for designing waveguide enhanced Raman sensors for bioprocesses. And okay, so what does it take to design such a sensor? There are quite a few components that are involved in a Raman system. I don't know why it's moving by itself. Sorry about that. And the first thing would be to decide to choose a laser. And again, I'm not going to have the time to go through every single decisions that we made, but I can quickly go over it. So in that particular case, we decided to use a 785 nanometer laser to get started, because it's a good compromise in terms of wavelengths between shorter wavelengths that would have a higher efficiency, but higher fluorescence as well, and longer wavelengths where the Raman cross section is not as high, but that may be more available and more powerful. Of course, we also need a spectrometer to do the detection. So both the laser and the spectrometer, in our case, are OEM components, are not integrated on the chip. And the choice for the spectrometer is dictated by the choice of the laser. So to collect the full Raman spectrum, we chose a spectrometer that goes up to 1150 nanometer. For the waveguide material, we need something that's transparent and that has low loss. So we ended up choosing silicon nitride. The waveguide geometry needs to strike the right balance between a high interaction between the evanescent field and the analyte, but also not have too high losses that are too high, so that the interaction can happen over long path lengths. And that's why we chose a TM strip waveguide. And finally, the coupling scheme is very important, because we want our chips to be used in an industrial setting. They need to be used by people who don't have the experience, and who don't, even if they had the experience, who can't afford the time to do expensive alignment. And that's why we decided to fiber couple or Raman chips, so that they can be easily transported and used in the field. And so at the end of the day, here's a picture of what one of our prototype looks like. So it's a tiny chip of roughly 5 by 5 millimeters, packaged with a fiber array. That in that case, it's really annoying, but the slides are moving by themselves. Sorry about that. And in that case, we packaged it in. We integrated it in a flow cell for measurements, and I'll show you another integration in a second. So now, let's see how that can be used in practice. So this is a project where we worked with a lab from AgroParisTech here in France, that was designing a process and wanted to improve a process to manufacture picomeric acid, a molecule that you've never heard of. Don't worry, I also had never heard of it before this project. Turns out that it's an intermediate that's very used in the cosmetics and the pharma industry. Picomeric acid is produced through a fermentation process. And the problem with that process is that the target molecule, picomeric acid, is toxic to the yeast that produce it. So there is a negative feedback loop. The more you make it, the more you kill the yeast, and so the less you make it. Hence, the idea that our collaborators at URDAB had to implement a continuous extraction process to remove the picomeric acid as soon as it was produced by the yeast, and therefore not enter this retro inhibition regime. For that to happen, they needed a real-time measurement of the concentration of picomeric acid, which they couldn't do using chromatography. That's technology that they were using beforehand, because again, chromatography requires taking off a sample, running a half-an-hour measurement that has to be run by an experienced technician, because it's actually pretty tricky to do. And so it's something that they could only do a couple of times a day, and that was very labor-intensive. So definitely not suitable with real-time, with continuous extraction. And that's where we came in. So they told us they need to detect picomeric acid below 300 milligrams per liter to be meaningful for them. So what did we do? First step was verify that we can indeed detect picomeric acid with our Raman sensors. And we started by doing it in a buffer solution, so just in DI water, and we got a limit of detection of below 100 milligrams per liter. That was so well below the requirements. And also a very good linearity, which is a good sign for the models that we will need to build afterwards in a more complex medium. Here we built a first model already in DI water to predict the concentration of picomeric acid from an unknown spectrum, and we had a low root mean square error of prediction of 61 milligrams per liter. So again, well below the requirement. So this was done in DI water. It was reassuring. Of course, that's not the condition of the actual measurement. And so what we did then is verify that it still works in a culture medium where there is a yeast actually going to grow and produce. So we reproduced that in the culture medium by itself. So it's a YPD culture medium. It's a pretty standard. And what you can see here is a principal component analysis that lets us see how well we can distinguish between different concentrations. And we still had a good separation even below 300 milligrams per liter. So at that point, we were very confident in the capability of our sensor to do the job. And so we went and integrated it in that process. So here you can see the fermentation process running. I guess you probably get a feeling for how messy it is. And again, that highlights the need for a highly specific technique like Raman spectroscopy. And if we zoom in, you may be able to distinguish the light from our sensor measuring in real time what's going on in that bioprocess. And so through those measurements, we were able to ensure the good conditions for the yeast. And the outcome of that project was actually a doubling of the yields of picomeric production from our partners. So it was a very successful project in the end. And I realized that I didn't show you, but I think I removed the picture. But in that case, we didn't use a flow cell, of course, to integrate our sensor in the bioreactor. We had an immersion cell instead, where where we can't really see it here, but where the surface of the peak is exposed to the culture medium at large, and so it interacts with everything that's going on in there. And to finish, I want to tell you about why we are part of the ALUVia project and what's our interest to do Raman spectroscopy, on-chip Raman spectroscopy in the UV. So I did talk very briefly earlier about the pros and the advantages and disadvantages of various wavelengths for the excitation of Raman. One of the reasons to use a lower excitation all the way down to the UV is that the Raman cross-section, so the Raman efficiency, increases dramatically when we decrease the wavelengths. If we cut the wavelengths in half, we get a 16th time improvement in the Raman efficiency. So that in itself is already a great reason to use a lower excitation wavelengths. On top of that, we can get resonance with electronic transitions when we go to the UV. As you can see on the little diagram on the right, in, let's say, visible Raman, the excitation happens to a virtual energy level, and then the electrons go back to a different vibrational energy level, and so we detect this shift here between the different vibrational energy levels. In resonance Raman, that can happen in the UV when the energy of the incident light is high enough. We can excite to a real energy level, which makes the process a lot stronger with improvements up to 1,000 times. And finally, the last but not least, I should say, a benefit of going to the UV for Raman is to decouple the fluorescence and the Raman response. Because autofluorescence typically starts around 300 nanometer all the way to 1 micron. going to a region where the Raman spectrum is located before the onset of autofluorescence allows to decouple the two, and therefore to have a much more easy processing of the spectrum and not have to worry about the background that fluorescence represents for Raman measurements. And so yes, that's a motivation for us to go down to 266 nanometer as part of the ALUVia project. And the results from the platform Sonia already showed you earlier. And so yeah, we're very excited to get our hands on one of those chips and make a Raman sensor out of that. Of course, a lot of this was collaborative. So the entire Inspect team, we had our collaborators at AgroParisTech and from the ALUVia project, and from our scientific co-founder and advisors, JJ and Laurent Vivien. Yeah, thank you for your attention, and happy to answer any questions.
That was another very interesting presentation. Thank you. Is there any questions from the audience?
Okay, Jerome, maybe I have a question. Thank you for the nice talk. This is probably the 5th or 6th time I heard about you speaking, but every time I learn about something new. So one question is that for Raman, we know that there typically has a lot of background signal coming from both Raman signal from waveguide and also fluorescence. So I'm curious, how do you get rid of the background?
So they are different, or it depends, I guess, which background we're talking about. So there is a background, the background from the cells. For example, this one is also from the cell or from the medium. The fluorescent from the medium, this one is hard to get rid of, just because it's, as soon as you're making a Raman measurement, it's there automatically. There are some tricks that people have used, such as shifted excitation Raman, where we acquire two Raman spectrum with a slight difference in wavelengths, and because the fluorescence is not influenced by the excitation wavelengths, we can then subtract the two to get rid of the fluorescence spectrum. This being said, the fluorescence is still there, and so it's still going to contribute to the noise, to the shot noise of the photodetector. So it's more of a trick than really getting rid of it. Then there is a different kind of background, and I'm thinking if I don't have a good slide explaining that, unfortunately. So it's hard to illustrate it. There is also the background from the chip itself. Again, this one is hard to get rid of because essentially we're doing waveguide enhanced Raman. We do need to have the light propagating in a waveguide. Here, the solution is to filter out as much as the background, the closer as close as possible to the sensing region, so that the only background that we have to have, we don't really have the choice, is the one from the sensing region. Everything else we can get rid of. That includes, for example, the background from the fibers that are used to couple the light to and from the chip. Obviously, that's pure noise and pure background for us. And so this one we can filter out through appropriate filters on the chip. Does that answer your question, Jeffrey?
Yeah, thank you.
And of course, maybe, I guess I should say that there are also we can also use algorithms to filter it out afterwards. It's post-processing, but again, it's not really filtering. It's more like removing it afterwards, but it still contributes to noise.
I think there's time for one final question before we close off this session.
I also have a question. I was wondering, so I don't know what kind of cross sections you deal with in the Raman for this Raman scattering, but are you concerned with multiple scattering since you have quite a long interaction length here? Is it possible that the spectrum that you get back changes if you increase this interaction length, or is it not a concern to you?
I'm not really sure what you're referring to. So different scattering, as in different scattering centers, or like
no, I mean multiple scattering. So light that is elastically scattered multiple times?
I guess we're not too worried about that because so the Raman scattering is very, 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 very weak. We're talking 1 photon in 10 millions. So basically we're pretty sure that if the Raman if the photon is a Raman is if the Raman photon is not collected right away by the waveguide, it's basically lost. Right, okay. There is very little chance that it scatters again and that we collect it, and therefore we really collect. And that's one drawback of waveguide enhanced Raman that we need to be clear about. We really measure what's going on at the surface of the chip. We're not able to detect what's going on too far away from the waveguide. Let's say probably further than 100 or 200 nanometer is probably too far for sensors to detect.
Yeah, so
does that answer your question?
Yeah, but if you move to the UV, you said that the cross section will
yeah, that's true.
increase. So, but still, it's neglectable. The amount of so the second order effect will be neglectable in your case. What you expect?
Yeah, I guess we don't expect it to be the case. People have done it. The good thing is that we can piggyback on everything that people have done in free space. So people have done UV Raman in free space, and they've had that's not an issue that they've had as far as I know. They've had different issues with intensity that of course gets much higher in the UV and power densities, stuff like that, but not with multiple scattering as far as I know.
I see. Thank you.
With that, I think we've reached the end of this webinar. I would like to use this moment to advertise our upcoming session, because there's another one coming up in September. On September 19th, there will be another session that focuses on health applications. We are still looking for one speaker, so if you feel like you would be a good fit for that, please reach out to us if you want to contribute. And with that, I'd like to thank you all for attending today's session, and especially our speakers, Sonia García Blanco, Professor Juejun, and Jerome Michon. Thank you.